Professor Beaucage, I don't think any of your audio's coming through if you are talking. I don't know if you can hear me.
Can you hear me now?
Yeah, I can hear you now. Thank you.
That's good. All right, you can hear me now, right? I just hit it 2 times.
Yeah, I can hear you. So it should be also recording on the.
Okay, all right, that's good. Thanks. Sorry, but yeah. So anyway, the mic was turned off inside the inside panel.
Gotcha.
Anyway, so the this is kind of a funny area in a sense, like because polymer composites have been around a long time, like at least since the beginning of polymers. It's like the first thing was like, I mean, for rubbers, like tires, you had like carbon black. Without the carbon black, the rubber just rips apart. It has no tear strength at all. It's just like a pencil eraser. So if you put the carbon black in, then you get a tire, right? So it's in tires 60% carbon black. So it's basically carbon black with a little bit of rubber binder, and it's a 30% oil and 10% rubber. So even though it bounces, it's kind of mostly carbon black. So the carbon black is a nanoparticle. It's about 50 nanometer particles that are aggregated. So it's been around a long time. In fact, a lot of the stuff about, I'll tell you about shifts in glass transition with interfaces and with filler content going up. That work was done like in the 1940s in Russia and in the US, like during the Cold War, 50s, I guess, during the Cold War kind of. So anyway, so a lot of the stuff was already done, and then kind of, I guess about 15 or 20 years ago, it was kind of rediscovered or something. And then people started doing this kind of more controlled situation, I guess, more or less. So it's a little bit of flim flam going on in this, in a sense. Although, so the point of it is to try to get it to look more sciencey. So you have, I mean, if you can, here, did that work? Anyway, so if you have like a phase diagram for like water, so you have like pressure.
Dr. Beaucage, is there any way that you can turn those lights down? Because it's kind of so bright that we can't see you writing.
Yes, there is. There definitely is. You can point to the ceiling. That's right, to turn it down. There's probably a way to do it. Lamp. There. Well, the lamp just went out. Is it off okay?
It's still pretty washed out. Is there like an underlight?
No?
Like
Yeah,
a
there is an
paper?
underlight. The underlight's off.
That's better.
Okay.
Yeah.
That was auto.
We can see that.
Anyway, so you have like, I don't know, you have low temperature, you have ice, and high temperature, you have water, you have steam. So whatever the phase diagram is. The other one is probably like pressure or something. I can map it out, but so you have a phase diagram. Then we had a phase diagram of like temperature composition for like a UCST system. So that's spinodal, binodal. This is one phase. And then you have this phase diagram for block copolymers, which is something like this, where this is the block, the AB fraction, like the 5B of the AB block. So you change the length. You get a small B and a large A. Then you get these different, in the middle is spheres, and you get cylinders. You get lamellae. somewhere between cylinders and lamellae, you get this double diamond. Just self like a network structure. Anyway, then that also has a critical point. This is temperature, this is kind of composition. Right? And then if you go to surfactants, right? So you have this, like this is 12 carbons, and this is a sulfate. Sodium, I guess that's minus. Sodium sulfate, SO3, and A+. Then that thing will form. First, it could be soluble at high temperatures. Then there's what's it called? There's a temperature where phase separate. Then you can make spherical micelles. You can make worm-like micelles. You can make lamellar kind of sheet micelles. Something just like the black copolymer you can do with micelles. Right? So the water is an atom or a molecule. This is polymers. So some question of can you have a phase diagram at some point? Like bricks don't have a phase diagram. So you have the building made of bricks. They don't have a phase diagram because they don't move around with like KT energy. So as you're going down in size, at some point where, so this is called kinetically controlled because you have to lay the bricks by hand. That's kinetics, right? So if it just kind of self-assembles, maybe like water self-assembles into a crystal, that's because there's KT energy and there's enthalpic. So that's like the entropy and then the enthalpy of attraction, and they organize because of that balance between those two. Right? So you have like the melting point is the enthalpy over the entropy. The transition enthalpy over the transition enthalpy is the melting point. And so, and similarly, you can kind of talk about polymers that way. And you can talk about the polymer chain is moving around, like each of the monomers moves around with the KT energy. And then the micelles kind of have that same behavior in a sense, right? So, but nonetheless, like this is definitely thermodynamics, and this is definitely kinetics. And with things, there's a continuum between the two, and at some point there's a borderline, right? So nanoparticles are definitely at that borderline because they're going to be, they could be 100 nanometer in size, so they might not be really moving around with KT energy anymore. They might be like bricks, or all right. So the advantage of that is that here, like if the thing's immiscible, it's immiscible. Period. You can't make it miscible, right? So it's stuck. Right? So you can only use thermodynamics to make the thing miscible. And to make it immiscible, you can use thermodynamics to do that. With bricks, you can only use kinetics to build the house. You can't use them, it's not going to self-assemble a house, right? But when you're in this kind of never land between kinetics and thermodynamics, it's possible to partly have it self-assemble and partly use kinetics. In fact, you basically have to use both to do it because it's not moving fast enough, so you have to stir it. Right? So nanoparticles are always going to have some stirring involved. Right? So, and the original in 1940, when they made tires, it was all stirring. Right? And then in 1990, it was all thermodynamics. And then they haven't exactly connected with each other. Right? So that's kind of the status of the nano composite field. You know, so it's got to have both. But you'll see anyway. And there's like kind of famous players in this, like Sanat Kumar just won the Polymer Ford Prize at American Physical Society. It's like the top medal. And he primarily worked with, or has worked with nanocomposites. So he's done some other stuff recently. So he started out in MIT undergrad. Then he went to like somewhere in California. Then he did a postdoc at IBM with Doi Yoon, who's like Doi Yoon was a postdoc at Paul Flory, so it's like kind of a lineage and handoff of Nobel Prizes. And there's, you know, like if you're close enough to a Nobel Prize, or like 2 generations away or something. So he's like 2 generations away. So he went to like Penn State, which is polymer place, and then he went to RPI, which is kind of more engineering-ish. But Linda Schattler was there, and she was doing a nanocomposite stuff, and I think she got him into that. And then he moved from RPI to Columbia, like in 2000 something. And then he turned this nanocomposite into the main thing he was doing. This guy, Ben Nikowitz, is at South Carolina, and he was like Kumar's chemist, kind of. Although he's done a lot on his own. Baya's at AFRL in Dayton, and he's the director of it now, for the research branch. So he did originally did clay nanocomposites. Like when people first started getting into this, like they saw you could have clay, you could have single sheets of clay, you can exfoliate it, you can break apart the sheets. And then the idea was, all right, it's dirt, so it's pretty cheap. Then you can make nanoparticles from it kind of easily with some chemical treatment. You can also make synthetic clay that's already separated. So you kind of force ions in and separate the sheets with the ions. That's kind of the idea of it. So you put an acid in and it'll break them apart. And you can take those exfoliated, so foliation is like trees, like leaves, and then exfoliation means you break the leaves apart. So you're breaking off these layers. Exfoliated clay can kind of mix into polymer, and there was one product that Toyota made, which is an underemployed application of nylon, where they put clay in it. It was more like a novelty than an actual useful thing. And then, other than that, there hasn't been much use of clay in polymers, even though it's cheap and it's nanoparticles, because other problem that all these things have, if they cluster, like they have so much surface area, they just clump up. Right? So how do you break apart the clumps? That's the main theme of this stuff. Anyway, so, and then there's all the traditional things, like, so every time you blow a film, it's got some kind of silica powder on it, nanoparticles, to keep the layers of the plastic from sticking together. Right? So, and silica is thrown into everything. Titanium is paint. So this is nanoparticles, and it's in a polymer binder. So basically, all the paint on the wall is made of nanoparticle titanium, which is also photocatalytic. So you can use titanium to burn off carbon, soot, and things. If you paint the walls with the right kind of titanium, which is you just make in a flame, then it'll burn the soot from cars and things. And it can also be used to make hydrogen, split hydrogen and oxygen under the right conditions. So basically, you can use that. In fact, Dion Eces and the environmental has kind of made a living off titanium, photocatalytic, whatever. And so is like everyone else. That guy's got 600 publications, it's a lot. And last year, he published 75 papers, which is like, I don't know how many that is a week, but I mean, it's a lot of papers. So he's kind of a mild-mannered character, but he's got a lot of stuff going on, apparently. Anyway, so barium titanate, we talked about, that's the for capacitors, right? And then cadmium selenide and cadmium serenide or something. These are magic solar absorption for solar cells. Like they perfectly match. They perfectly match the solar spectrum. Unfortunately, cadmium is deadly toxic. So it's like a tetragen, it's a neurogen, it's every kind of gen that there is. So you can make a lot of, and there's a company in Toledo called First Solar, I think, that uses this stuff to make solar panels, like flexible solar panels. So you deposit this. Anyway, but basically, you're spreading around cadmium all over the world, which isn't a good thing. But on the other hand, you get free electricity from it, so maybe it is good. It's a low temperature process. So it's a nanoparticle cadmium. These are for solar panels. C60s also for photovoltaics, but it's like it's a current collector in a polymer photovoltaic. So you put in something that absorbs light, and the C60 carries a charge away. So, and it's also been talked about as some magic dust that could make everything better in terms of mechanical properties. This is magnetic. So this is like for medical application where you want to, people will inject iron oxide, and then the nanoparticles you can heat up with a magnet. I mean, if you put a magnetic oscillating magnetic field, and they'll heat up in the spot and you can kill the cancer. Well, I don't think that's ever been used, but people, there's like umpteen studies of that. You can also put it into polymers. Zirconia's got optical features. This is ITO is it's like a conductive coating, you know, for like on your cell phone, there's ITO in it, so you can touch it, touch screens and things. Also, solar panels, the top of it is ITO. So there's all kinds of nanoparticles. So to miscibilize them, people stick stuff onto it, like silane coupling agents, phosphates, amines. And then you could also put functional agents like some kind of drug on it. This is a typical Air Force AFRL kind of slide. So this is from Via, this thing, from this paper. I mean, this is how they put things together. They have a whole team of people doing this stuff. So it's kind of nice to have this. So basically, everything's here. They use it in fracking fluids. So, I mean, nanoparticles. So anyway, so, and then they show like, boom, tires, you know, so this isn't how they make tires at all. Tires is like the classic thing because it is nanoparticles, but there's no monodispersed particles in a tire at all, ever. You know, there never was and there never will be. So like the idea that you can go from this to that is kind of nutty. You know, I mean, so you have to kind of be careful about oversell the stuff. Anyway, so see if this works. Yeah. So this is the kind of thing what I mean by a phase diagram. So everybody wants a phase diagram. This is 2012. You'll see like it flops around. There's this phase diagrams kind of it's a way to get rid of that guy. This guy can do that. This guy. Anyway. So this is the typical thing. Like these are particles that have grafted bimodal polymer brushes. So this polymer stuck to the surface that matches the matrix. So this is like kind of the original of this was silica, which you want to put into a tire because you get like green tires from that. The rolling resistance is much better. So they're much more fuel efficient. So they wanted to the original idea was compatibilize silica, which is inorganic, with the rubber, which is organic. So they put silane coupling agents on, and so that's basically a SiO, like a sol gel reaction. So you have like there's hydroxyl groups on the surface of silica, and they react with the hydroxyls in this coupling agent, and it spits off water. You get an SiO bond, like a glass bond. Then you can have an organic on the other side of it. So you can have whatever butadiene rubber or something attached to it. Anyway, so that was, and then you can put long chains onto that too. So you can couple anything onto silica with it, just a condensation reaction. It's just a pH-driven reaction. You can do it in your bathtub if you want to do it anywhere. So basically, it's really simple to do. In fact, bathtub caulk has sol gel reactions going on like that. So just as it cures, it makes silica in situ from it. So anyway, so you have, so this is grafting, but here they're grafting some kind of, and this is Linda Shatler. She's now, I think, Dean of Engineering at University of Vermont. And then she was at RPI for a long time. And then this is the guy, the chemist that does the surface grafting from South Carolina. Neely, I think, is someone, I don't know who he is or her is, she is, and the other people I think are grad students, I'm not sure. Anyway, so all these papers on a site have like 1,000 citations. Like they're all like hugely cited papers. You know, so this is cited because it's got this phase diagram, it's predicted. This is the number of graphs per nanometer, like 40 per square nanometer. You can see here chains per nanometer squared. And then this is a ratio between the size of the polymer and the matrix and the size of the nanoparticle. Right, so that's also, it's called alpha sometimes. And this is called alpha, and that thing is called rho, usually, like Greek rho. So anyway, so if you have big particles, they separate out. Aggregates means it's like clumps, right? So that's not useful. And then as you make the particles smaller, they disperse better. Okay, so this is a characteristic of diffusion-driven dispersion. Or smaller things mix better. This isn't your normal experience because if you take powder sugar, you try to mix it into something, it just clumps up. If you take granulated sugar, it's really easy to mix it. So this is a signature of thermodynamic mixing. I mean, diffusion-driven mixing. And the other example that you're used to is kinetic mixing. Right, so the two completely different behaviors. Like it's really hard to mix fine-grained stuff into something, especially something viscous like a polymer. It's really easy to mix big things into it. I mean, relatively easy. Right? So basically, when you see a map like this, you're kind of looking at something that looks like molecules. Right? So the difference here is that it's forming structures on the road to that. So that's why this is cited so much. So they have micrographs that show that there's these structures that form, and they can, by taking different TEMs and slicing it in different directions, they can tell the difference between a chain and a sheet. The micrographs here aren't that convincing, and that telling you that this is a sheet and that's a chain, that there's a definite point. We can tell the difference between chains and sheets from TEM. That isn't convincing either. And then the idea that at some point you get to disperse. So this whole thing is pretty wishy-washy, but it's desirable to have a phase diagram. So they did it. You know, they made a phase diagram. So that's kind of the idea of this. The greater the so as the particles get larger, they get less thermally dispersed, and as the grafting gets denser, they become more dispersed. So it's kind of like what you think. It's kind of verifying somewhat what you think about it. Right? So that's good too. It's not so much unexpected. The fact that you have these regions where you have some kind of different structure showing up is unexpected, I'd say. But there's this explanation for that. So the idea of that is this. So the idea of that's pretty hokey. I mean, I guess I don't necessarily believe all these things. So you have your stuff. It's got some kind of things on it, right? And that they're dispersed at some point. But so if you get the concentration high enough, the way the story goes is that because these are both like hydrophobic or whatever, hydrophilic, they'll attract and they push these arms over. Right? And then there's an entropic barrier because these things are straightening out. So they have to straighten out to kind of get crowded there to the curly over here. So there's a balance between this, you know, they're happy to be together, but they have this penalty that they have to make these things stand up straight. So the battle between that is going to decide what they'll form. This seems to be completely bogus to me. Like there's not, one thing you can do, you can measure the size of these things, like with neutron scattering, so you can tag these in some color. And you can do neutrons. So you can imagine the kind of things you could do. You can tag those things red, and you can say, like, what's the size of those things? What's the size of those things as a function of like concentration? You find out the size goes up. And then that's proof that this happens. I mean, maybe it's proof that it happens, and could be, but.
Sorry, the size goes up as a function of
Of
their
yeah, so if you-
concentration or the
concentration
concentration of the.
concentration of the smiley faces.
Okay.
So the more smiley faces you have, then the chain on the outside of this thing increases in size. Right? Usually it's like some ratio of the initial size. I'll show you some things that show that kind of behavior, but I don't know. The fact is that the questionable fact is that they form strings, kind of. They have something kind of form strings and they get larger. I mean, so you can see, you can get to somewhere with it. Anyway, that's worth 1,000 citations to do that, right? So it's kind of where things are. It's bad to have a skeptic show you stuff, you know. So this is Sanat Kumar again, right? And this is just showing. So that, all right, the original idea. So this idea came from 1940, right? The idea that you have bound rubber. You could find that there's a thing called the DBT measurement, which you take your filler particle and you put like an oil on it, and you see. Then you drain the oil and you see how much oil is stuck to it. And the weight difference is this DBT measurement. So they said like rubber is like oil. In fact, the tire is almost like largely oil. You know? The tire is 40% oil. So it's got oil, a little bit of rubber, and then a lot of filler. Right, so the DBT measurement is kind of valid because then you can see like at least how much oil actually sticks to the carbon black. But supposedly the rubber also sticks to the carbon black. And there's some evidence for that. Right? So this is kind of believable. So anyway, so the chains, so he's gonna have this nanoparticle, then like this layer on it. So how do you measure how big is the layer? You can take those particles after you absorb the polymer and then measure the hydrodynamic radius. So it has a hydrodynamic size. You can take the particles and then put them in a TGA and see how much mass you burn off. Take the density of the polymer when it's in a bulk and say that's going to be the thickness of the thing. That's his TGA thickness. And then he can simulate it. So one of these guys is a simulation. Sanat Kumar's actually did simulation for his PhD, so he's probably did the simulation. I mean, it's just this lamps thing, so you just plug it in and it does it for you, you know. So anyway, so he plots that out and gets like kind of the dashed line is anyway. Dashed line is a neutron scattering measurement for the size of the thing, and then TGA measurement gives this thing, and then he does a calculation with Flory-Huggins equation, which I'll talk about in a little bit. And then the solution is the hydrodynamic radius thing. So hydrodynamic radius matches with the calculation and with the measurement doing neutron scattering. The TGA is a little bit lower. So people want to know about this interfacial region, because if you go to measure the glass transition of the filled polymer, the glass transition shifts and it can go up or down depending on if it's favorable or unfavorable relationship with the surface of the particles. So if it's favorable, then the polymer gets stuck to it and it can't move, so the glass transition goes up. And if it's unfavorable, it's repelled from the surface and somehow it goes down. The down part, I don't think maybe it's not that well explained why it would go down, but it does go down, sometimes more significantly than up. This is the same kind of group like Shadler and Kumar when they were both at RPI. This Ben Nikowitz, who's at South Carolina, who's making these surface coatings. This is just designing the interface. This supposedly shows this interfacial. I mean, I guess the middle is a fiber, and then this outside part is a coating, but it's kind of hard to tell. It's a TEM. It's an SEM of a nanotube polycarbonate fracture surface. So it's kind of hard to tell where your stuff is here. Anyway, so this is just what Linda Shadler is saying, like why you'd want to use nanoparticles. So I mean, the interface can change the bulk properties, because if you get small enough particles, the whole material becomes interface. So if you tune the glass transition with this interfacial properties, then you can tune the glass transition of the whole material if you put enough of those particles in. And then, some of the particles have special properties, like nanotubes can be really strong. So the idea is like you put in a small amount of nanotubes, get a big increase in the modulus. And then you can tune with the defects that are introduced, you can tune the optical, electrical, whatever. Right. So and this is like the capacitor thing. So it's basically she's got these three. There's other reasons why you'd probably put nanoparticles in. But usually it's like cost benefit, like you should be looking at Why does this thing say no video? Maybe that should be on. I noticed that before. All right, so this is the TG thing, right? So it's comparing, this is from that same paper, from this, it's like a review paper. But so you can also get a shift in TG if you just spin coat a polymer onto a silicon wafer, and then you can do ellipsometry and measure the shift in glass transition by the change in the index of refraction. You can do that with neutrons with X-rays too, right? So anyway, so it's possible to measure as a function of the thickness of a film, the glass transition. And so like a SI wafer has a surface layer of silica, SiO2, because it's an oxide. Right, so and you can put SiO2 particles in a polymer, so you can do both. So this was, I don't know what 31 was, but exactly the same thing was done in 1950, you know, by a Russian guy by the name of Lipatov. He did a lot of polymer work, but so basically there's nothing really new about knowing that the glass transition shifts when you put a lot of filler into the system. So in this case, with silica and polystyrene, it's a reduction in the glass transition. So that's an unfavorable, that's like an unfavorable situation. Right? And the same thing happens in a nanocomposite. The same thing happens in a composite. If you put in just bricks of silica, you get the same behavior. Right. So anyway, so that's TG shift is one thing that people say is due to this like bound rubber business. So you have the chains that are stuck to it. TG would go up if they're stuck, and somehow it goes down if they're not stuck. Right. So they've worked out like it's a favorable condition. So you can convert the TG shift to the del parameter, which is like the chi parameter. The difference between these things squared is the chi parameter. So this is the Hildebrand del, like a number that says if things are going to be miscible. When that's 0, they're miscible. When that thing has a positive number, they're immiscible. So basically, this is using thermodynamics to talk about what could be kinetically mixed systems, right? Zinc oxide and polystyrene. And then basically, this is the wetting region, and this is the non-wetting region. So you have a point where, in terms of this TG shift, which is controlled by the particle size, so the spacing has to do with the loading and the particle size combined. And then, so the TG shift is going to decide how the thing's going. So you got to, it's kind of pointing to the direction you're going to have a phase map. It's going to have composition, it's going to have particle size, and it's going to have like the wetting and de-wetting is going to decide like what structures you can get from that. How to, what kind of features are going to come out of that, and what the properties of that thing are going to be. This is showing. So they can take. So you can take filler. So you can take filler and put it into a. Right, so normally you take, so you're going to measure like scattering intensities, you shoot at the sample, reflect over the pattern. Here you get the intensity as a function of scattering vector Q, and then normally it would be a polymer, so you'd say like it's -2, that kind of curve. Put in another polymer, it's going to be like 1 over I1 plus 1 over I2 times their volume fractions plus chi times the volume fractions equals 1 over the I that you get out of it. So it's called the Reagan phase approximation, RPA equation. So we can measure chi. So what this means is that if you have that pattern and the other one's the same pattern, this means that since it's 1 over increases, the number decreases. And these things, I is small in here, so this I dominates out here. In other words, 1 over I is large, I is small out here. So that these things dominate in this region. And this thing, which is large, dominates down here. So that, and it's negative because it's making 1 over I get larger. So means this thing diminishes as you increase miscibility. Because it becomes more miscible, this thing drops. As long as you have I to have a composition here. Right, so from that you can get chi, or you can get A2, second virial coefficient, like 1/2 minus chi. So basically they're measuring chi. This is for polymer. Polymer, if you instead of polymer put nanoparticle, then you can get the same thing. You kind of get the same thing. You get this chi parameter for nanoparticles. Right, so that they're doing kind of neutron or X-ray scattering. If it's silica, you can just do X-rays. Then you can measure this this chi effective for that thing, and you can say, well, this thing normally chi negative means that it's miscible, but here it's small number, so because it's like -1/2, basically this is miscible. Right? So there's an extra number. So A2 positive means miscible, and it's 1/2 minus chi, so chi negative means miscible. So makes A positive. But there's this other shift factor that has to do with excluded volume, right? So anyway, so basically these are kind of miscible systems, like they're a low number. 10 to the minus 2, 10 to the minus 3 is kind of miscible, and 10 to the minus 2 is on the borderline. So as you go through the length of the chains on the surface, so the longer the chains, for this case, this is in a, doesn't say, I think it's like 100,000 gram per mole. There's no units on this anyway. So basically, you're at sizes that are smaller, so that the chain length on the surface is smaller than the matrix length, and you're growing that length on the surface, so it's approaching the matrix length. As you approach it, the miscibility increases because chi negative is more miscible. So as you get longer chains on the surface, as long as the matrix is larger, then you get this reduction in the chi, which means it becomes more miscible. And then these are RP is the particle size, I think. It's not unity here. Sigma is the surface coverage. So these are different surface densities, chain density. It's a simulation result. That's why it's like not without units. And then each of these are different particle size. The smaller particles are mixing better. The higher the surface density, they mix better. And then as you put more chains on the surface, longer chains on the surface makes it mix better. So there's 3 things: particle size, small ones mix better, longer chains on the surface mix better, and higher surface coverage mixes better. Right, as long as you're within a certain range of this thing. So it has to be that your chain length is shorter than the matrix length, because once the chain length gets longer than the matrix length, this thing changes, like this situation changes. So that means you kind of need to look at the ratio of the surface grafted chain and the matrix chain to do this thing. That's the same thing about the wetting, de-wetting. This is as a function of, so that's the graft molecular weight. So this is, if you have a molecular weight of the matrix of 110,000, then you can see, like, as you approach, it goes, when this thing gets larger than that size, then things get bad. Like it becomes de-wetting. When it's smaller than that size, then it gets wetting. Right? And then this thing is the weight percent in the system, so it's exacerbated by the more filler particles you put into the thing. So anyway, so there's a lot here of just like qualitative kind of looking at it. So it needed to be kind of organized into this kind of phase map sort of thing. This guy, it's got to go somewhere. This is Mackay. So he's the first guy. So Mackay was a guy who was from Delaware, who went to Australia, became a professor there. And then he moved to Michigan State and became a professor there. And this Tutijik guy is a guy from Michigan. I don't know Duxbury and these other people. Van Horn is a guy, I think he's at NIST or something, or Oak Ridge. And then the rest of them. So anyway, I mean, McKay, this is the paper that he made his name on. This is also a 1,000 citation paper. So he's got three kinds of nanoparticles. He's got buckyballs. They're all in polystyrene. Okay? He's got buckyballs, C60. I think you guys know what buckyballs are. Right? So anyway, then he's got these weird polyethylene branch things, which he calls a nanoparticle. That's really like a polymer kind of. And then he's got polystyrene that he puts into polystyrene. So he's got a cross-linked polystyrene beads that he mixes into polystyrene. Because polystyrene is deuterated, his beads aren't. That means you can see it. Otherwise, I guess it would be invisible, right? So, and also it makes you wonder exactly what it is. You know, he doesn't worry about that feature of it. So, anyway, so the polyethylene, I guess you can see it. Let's see, is B. Yeah, so I guess you can see it in TEF, the index difference between polyethylene grafted and polystyrene. It's kind of hard to believe, but I guess you can see it. There has to be an electron density difference between the two. They were the aromatic rings that's there. And then with the neutron scattering, you can deuterate the polystyrene, so it's not a big deal. So this is C is the polystyrene mixed with polystyrene. So what he sees is that if he has different molecular weights polystyrene, he can get mixing. I mean, he can get, so he's got a power law, which means the surface of these polystyrene nano beads. And the beads, this is a Guinea regime, so you can see the beads are separated. So the beads are floating around in the polystyrene. Then when he puts it in a 75,000 molecular weight polystyrene, the beads clump up. So the higher molecular weight, right? So there's problems with kinetics here, right? Because it has to be made somehow, right? If you're mixing it and it's a high viscosity polymer, it kind of makes sense that the beads would be dispersed more because as you mix it, you impart a lot more energy in it, for one thing, with a high viscosity. And also it's entangled, right? So it's going to have like a network in it. And the beads, depending on the relaxation time for the network and the motion of the beads in the polystyrene matrix, those two relaxation times, it turns out the beads move faster than the chains relax. So the beads just see the network as a permanent rubber network kind of thing. So they're kind of stuck there. So no, he mentions the kinetic feature in this paper, which has 1,000 citations, more than 1,000. So basically, he's making a thermodynamic argument in the end of this paper. I think it's even general strategies, but what he means is thermodynamics. It's like he's taking these three systems that are completely different. He's trying to find universal behavior. So one thing he finds is that if you take the rate of gyration of the polymer, so the matrix polystyrene, you measure that with neutron scattering by deuterating like 1% of the styrene. So it's a lot of neutron scattering work. So basically, you deuterate 1% of the styrene, you have mostly hydrogenous polystyrene, and then you have the styrene beads. You can look at those 1% styrenes and see how if they swell or shrink when the particles are present, right? And it turns out they swell. So they swell when the particles are present. And in a continuous way, it's linear in the composition, like how much put in. And then if you make an argument that this has to do with the volume compression of the particles, then this comes from Flory-Huggins theory. This 1 plus phi would be like a miscibility. It's the excluded volume. He gets this term out of the Flory-Huggins equation as the excluded volume. Takes a cube root, and that would give him the dependence of this chain size due to excluded volume from the beads being present. And that doesn't match the data. Empirically, he finds that it's linear in the composition, which he doesn't have an explanation for, but he uses later to do thermodynamic calculations. So So you get this kind of behavior that the chains are changing, the matrix chains are changing size as you add filler to it. And it's not that much filler, right? It's like 10% volume fraction is the maximum in this thing. So anyway, so he gets, he's studying these three systems. The larger chains, the system's dispersed. And then there's this swelling going on of the matrix chains in this thing. So from this, he's going to get, like, he wants to get a phase diagram out of this, right? So one thing he says is that kinetics dominates the thing, and the only way to get them to go miscible is to go through this weird thing where he puts them, right, all these studies with these particles are solution cast. Now, there's not really any industrial process of solution casting from dilute solution to make a product. I mean, there's not really much. Teflon fiber spinning, I guess, use sulfuric acid, but it's not exactly the same thing. So basically, they're using a process to make these things that's inherently not natural, and also it's got a lot of kinetic features to it that aren't really accounted for. Like you make the solution and you spin cast it. So in his case, I mean, he makes a point of talking about this. So he says the only way to get this to go into a single phase for the C60, first, you can only go to 2% C60. If you go above that, it phase separates. And the only way to get it to go in is you put it into a solution, what solvent he uses, but then from that, he spins fibers out of it to quench it immediately. Like the solvent goes away right off, and he locks it into that structure, right? So that's how he makes his miscible systems. You know, it's a totally kind of kinetic process. And then, so then he goes through this routine that if you have the normal mixing of polymers, the molecular weight times chi is what he calls the chain insertion enthalpy. Like to put one polymer chain in, that's the enthalpy associated with it, because chi is per monomer, n monomers times chi gives you the enthalpy of insertion. He says that when you insert one nanoparticle, it's going to be the area of the nanoparticle times chi. It's going to be proportional to that, which is going to be the particle size squared. That was the surface area. So then he mentions that it depends on processing this thing. So he ends up with this idea that if you take the Flory-Huggins equation and take the first derivative to get the binodal and set it equal to 0, then you can get this expression. So log of the volume fraction goes with the chi parameter, comes out of that. So if he plugs in his magic chi parameter thing with the area, then he can get the critical binodal volume fraction is like that. And he says because he can only get this to mix up to 2%, that's his binodal number under whatever condition he made it. So he can get a chi parameter. The chi parameter he gets from that, he can get the energy of interaction between the particles and the polymer. And this is a really small number. It's 0.02 electron volts per nanoparticle, small. And the chi value matches up with, the chi value is like lower, it's polystyrene beads in a polystyrene matrix. So that normally has a positive chi mixing, is a deuterated polystyrene matrix with hydrogenous polystyrene as a positive chi. Those are immiscible somewhat. But his is negative chi, so his is miscible. So by putting the polystyrene into this bead form, he's made it miscible with the deuterated matrix. And then from that, he can kind of predict you can predict a phase behavior out of this thing. So he comes up with this scheme to explain why these beads are separating out. Let's see. This is his phase diagram. So this is the first kind of real phase diagram for polymer nanoparticles. And so this is the size of the polymer that's going in. This is the size of the particles that are going in. And he finds out that if those two match, that's his critical point. That's like where he gets phase separation. So if you have big particles, they're immiscible. And if you have large polymers, they become miscible. Right. So this is basically something like a diffusion led mixing process, because big things don't mix small things do mix. So that's diffusion. It's not kinetics, even though the process he uses is highly kinetic process. So it's kind of weird. And then he maps that out with neutron scattering and with TEM measurements. And then he comes up with this scheme to explain why this is happening, like why this thermodynamics happens the way it happens. So these are his beads. These are his polystyrene beads. He says that as they approach, so the van der Waal, they're approaching, they're interacting by van der Waal interaction, which is a short distance interaction. That was the idea that there's spontaneous dipoles in the bead surface, and then they would induce then there's a spontaneous dipole in the other one. Sometimes they go so that they would be opposite and they would attract, and sometimes they go so that they're in the same direction, they repel. When they attract, they pull in closer, so the distance is shorter, and this thing is 1/r², so the attraction ones win over the moving out ones. That's the van der Waal interaction. Right? So basically, it's a short range interaction. You have to be close to this thing. So 1/r². It actually relies on a rapid decay. So because of that, if you have spherical particles, they have a region where they're going to interact that's just over this kind of strut thing here. Right? So that means that if you have large particles, there's not going to be much of that area. If you have small particles, there's more of that area. Then you get a particle size dependence to the reason that these things would attract and not attract. And also, like in that region, they're going to distort the polymer more. So somehow he has a scheme where he can explain this using thermodynamics. It seems to be somewhat contrived, but basically that's 1,200 citation kind of idea. So I don't know. We can kind of quit here, I guess. Yeah, it's a good place to quit. So anyway, so if there's questions or anything, I can answer them. But basically, so I'll go through some more nanoparticle stuff next time and find a paper. Then it'll be like finals week. Turn it the last one. We'll do like individual. Just turn it. So it's kind of a deal. So is that okay?
Wait, so do we have the one that we turned in this week, which is 13, and
Yeah.
then
One
turn
more.
in 14, and then we'll have the final?
No, that's
Oh,
it.
Okay,
There's just
sorry.
14.
Got it,
Yeah, there's 14, and it's like just individual.
got it, okay.
Yeah, and then I guess like Friday a finals week or something.
Okay.
Whenever, basically doesn't matter much. I think grades are due the week after or something. I should be around, so. All right,
Thank you.
thanks.